Hello everybody, my name is Danielle Weigel, and today we're going to be working through another Transport 2 homework problem. This video will be split into 3 parts, working through each of the problems. Let's start with the first one. In this situation we have a closed capillary container containing 2 liquids, H2O and D2O, filled up in equal halves of the capillary from 0 to 5 centimeters and 5 to 10 centimeters. We are given that the maximum molar diffusive flux is equal to 2.78 moles per meter squared seconds. We're given the molecular weight of both materials and the density of both materials. And what we want to determine is the maximum mass flux of the system. So let's begin. We can start out with our first definition. We know that the mass flux of the system is going to be equal to the mass flux, the summation of the 2 mass fluxes. And then we know that the mass flux of any component is equal to the mass concentration of the component times the velocity, the total mass velocity, plus the mass diffusive flux of that component. Going ahead with that definition, we can substitute that in for this right here to give us the mass flux is equal to the mass concentration of H2O times the total mass velocity plus the mass diffusive flux of H2O plus the mass concentration of D2O times the total mass velocity plus the mass diffusive flux of D2O. We know as a general rule that the summation of mass diffusive fluxes or molar diffusive fluxes will always end up being 0 in the end. So we know that the mass diffusive flux of H2O plus the mass diffusive flux of D2O is going to be equal to 0. Since we have those both in this equation right here, we know that we can cancel those out initially. Then we'll just rearrange the equation really quick just to give us a better starting point. The total mass flux is equal to the mass velocity times the sum of the mass concentration of H2O and the mass concentration of D2O. So we're going to look at our unknowns. We have these mass concentrations right here and the total mass velocity that we need to determine. We're going to start out first with the mass concentrations of both materials. A mass concentration in its definition is equal to the mass divided by the total volume. We're going to abbreviate that volume total. And we know that we're given the density of the materials. So we can go ahead and we know that density of a material is mass per volume. So since we know that the capillary is split in half and filled with both materials, we know that the volume of H2O is going to be equal to the volume of D2O, and the sum of both of those will give you the total volume. With that in mind, we can go ahead and rearrange our equations a little bit using the density definitions. Using this density definition, we know that mass is equal to the density of the material times the volume of the material. So let's go ahead and plug that into our mass concentration definitions. The mass concentration of H2O is going to be equal to the density of H2O times the volume of H2O over the total volume, which we know is equal to the volume of H2O plus the volume of D2O, or just equal to 2 times the volume of H2O, since those are equal. That, of course, we can cancel out, and then we know that the mass concentration of H2O is going to be equal to the density of H2O divided by 2, or 1/2 times the density. The same is going to be true for the mass concentration of D2O. It's just going to be equal to 1/2 of the density. That right away gives us the equation in forms of terms that we know for these mass concentration variables. So next we're going to have to look at the total mass velocity. The total mass velocity is equal to the summation of the mass fraction of the components times the mass velocity of each component. So we're going to have to find both of those for H2O and D2O. Let's start out with the mass fraction. The mass fraction is the mass over the total mass. So as we said before, we've already defined that mass is equal to the density of the material times the volume of the material. So we're going to go ahead and just stick that into our equations. So the mass fraction of H2O is going to be equal to the density of H2O times the volume of H2O over the mass total, which is going to be the summation of both. So the density of H2O plus the density of D2O. And we can pull the volume out of those because we know the volume of H2O is equal to the volume of D2O. That lets us go ahead and cancel those out, which will just give us the density of H2O divided by the sum of the density of H2O plus the density of D2O. The same, of course, will be true for the mass fraction of D2O. Volume of D2O over the density of D2O times the volume of D2O plus the density of H2O times the volume of D2O or H2O. Once again, we'll pull those out and get rid of them and leave us with this equation, the density of D2O over the sum of the two densities. And right away then we have our mass fractions, and so let's go ahead and find the velocity of each component. For this one, we're going to be using the equation of relating molar diffusive flux to velocity and mole fraction, or mole concentration, my bad. We know that the molar diffusive flux can be defined as the molar concentration of the material times the mass velocity of the material minus the total molar velocity. Similar to our last homework problem, since this is a closed capillary system, we can tell that the molar diffusive flux, the total molar diffusive flux, or molar flux, excuse me, the total molar flux is going to be equal to 0. If it wasn't, we'd end up getting a buildup of material in one part of the capillary, which wouldn't have it being reduced to equilibrium. Knowing this, we also know that the total molar velocity will be equal to 0, and that allows us to remove this molar velocity from the equation, leaving us with just the molar diffusive flux is equal to the mole concentration of H2O times the velocity of H2O. Should be H2O. And we already know this was given, and now we will be finding both the mole concentration and the velocity of, and we will use that to find the velocity of the component. So we'll find the mole concentration really quick. The mole concentration is equal to moles over total volume, similar to how we were redefining mass concentration. We already know that molar concentration is in terms of mass per total volume, and we were also given molecular weight, which is in terms of mass per mole. Using these two, it's pretty easy to see how we're going to get moles per volume total. We're just going to have to multiply or divide the mass concentration of the component divided by the molecular weight of the component. That'll allow us to cancel out mass and get moles per total volume. So then right away, we already have our definitions for mole concentration. We're also going to redefine or input our density instead of mass concentration, so we'll replace that with density of H2O divided by 2 times the molecular weight of H2O. And then the same can apply to D2O. So the the molar concentration of H2O is equal to the density of H2O divided by 2 times the molecular weight of H2O. Same can be said for the mole concentration of D2O. It's just going to be the density of D2O divided by 2 times the molecular weight of D2O. Going back to our original equation that we're using to solve the velocity of the component, we now know that that's what we want to find. And we already know molar diffusive flux, so now we can plug those into our equation, rearrange it. We know that the velocity of the components is equal to the molar diffusive flux of the components divided by their molar concentration. So let's plug that in the terms that we already know. The molar diffusive flux divided by density of the material divided by 2 times molecular weight of the material, which is of course just going to be equal to 2 times the diffusive flux, the molar diffusive flux of the material, times the molecular weight of the material divided by the density of the material. And once again, the same can be said for the mass velocity of D2O. 2 times the molar diffusive flux of D2O times the molecular weight of D2O over the density of D2O. Awesome. So now we have both of those velocities for each of those. And we use that equation. So now we need to find our total mass velocity using this equation right here that we mentioned at the beginning of 2. We also already redefined our mass fractions. So we're going to go ahead and just plug those into our equations. We'll put a little summary right here for our mass fractions. Mass fraction of H2O is equal to the density of H2O divided by the sum of the densities. And using that, we can go ahead and plug in our summation equations in order to get the total mass velocity. That's just going to give us the density of H2O over the sum of the densities times the velocity of the mass velocity of each component. So 2 times the molar diffusive flux of H2O times the molecular weight of H2O over the density of H2O plus the density of D2O over the density, the sum of the densities again, and then multiply that by 2 times the molar diffusive flux of D2O times the molecular weight of D2O over the density of D2O. Looking at that equation, there's a lot of things we can simplify. We can go ahead and get rid of these densities, and then we can pull out this part and this part. And then we also know that the molar diffusive flux of H2O is equal to the opposite of the molar diffusive flux of D2O. Using that identity, we can substitute this in for as a negative H2O, so that we can also go ahead and pull that out, leaving us with the total mass velocity is equal to 2 times the molar diffusive flux of H2O over the sum of the densities times the molecular weight of H2O minus the molecular weight of D2O. And now that we have the total mass velocity, we can plug it back into the first equations that we were working through. I'll just rewrite it for you. The total molar flux, or mass flux, excuse me, the total mass flux is equal to the total mass velocity times the mass concentration of H2O plus the mass concentration of D2O. We have definitions of these with our given terms, and now we have a definition of this with our given term. So we're just going to rewrite the equation, and you're going to see something really magical. We have that 2 times the molar diffusive flux of H2O times the sum of their densities times the difference between the molecular weights, also times 1/2 of the sum of the two densities. And once again, you're going to see some stuff canceling out. You've got the sum of the densities canceling out, your 2 and your 1/2. And that leaves you with the total mass flux of the system being equal to the product of the molar diffusive flux times the difference between the two molecular weights. So then we can go ahead and plug our numbers in. I'm going to have to go look at them because I don't remember them. 2.78. The molar diffusive flux of H2O is 2.78. Moles per meter squared seconds. And that one is positive because that's on our left side of the capillary from 0 to 5. So those will be moving in the positive if we define this direction as Z. If we define this as the Z direction, the water molecules will be moving to the right in the positive Z direction, while the D2O molecules will be moving in the negative Z direction. So the molar diffusive flux of H2O is positive, and the molar diffusive flux of D2O, if we had used that instead, would have been negative 2.78 moles per meter squared seconds. And then we know that the molecular weight of H2O is 18 grams per mole, and the molecular weight of D2O is equal to 20 grams per mole. So let's go ahead and plug those numbers in. We have 2.78 times 18 minus 20, negative 5.56 grams per mole times mole meter squared per second. That'll give us grams per meter squared seconds. And that is the answer to the first problem. When we look at this answer, you're going to think like, well, does that make sense? It's negative. Maybe that surprised you. So let's look at our capillary system. We already mentioned that it's a closed system. We have H2O molecules moving to the right in the positive z direction, and D2O molecules moving into the left in the negative z direction. We also mentioned that the total molar flux is going to be equal to 0 in order to to avoid a buildup of materials, because we know that the capillary, as it starts mixing, is going to want to go to equilibrium. Even though the total molar flux is going to be equal to 0, since the molecular weights of the two materials are not the same, as we discussed in the previous video, the total mass flux will not be equal to 0. Since we know that D2O is a more massive material per mole, and we also know that it's moving in the negative z direction, we look at this and we say, well, yeah, the total mass flux will most likely be negative, since we have the same number of moles of material mixing, and but a heavier, more massive material on the right moving to the left in the negative z direction. So a negative total mass flux would make sense. Have a great day. Any questions can you place in the comments below.